Good day, everyone. We're going to introduce another integration topic for you today. Now, this will be something we didn't do in the previous calculus class. This is just for Calculus BC students. We're going to define what an improper integral is and show you how to try and evaluate them. Let's go ahead and get started. I'd like to introduce the topic here by just revisiting this idea of measuring the area under this curve and actually defining a function that will measure that area. And then that area will be defined as an integral. We used this idea when we introduced the fundamental theorem of calculus. And we call this an area function. So we have one function or a graph of a function that we wish to measure the area underneath from some fixed number out to some other arbitrary number. And so I'm going to write this and call this blue curve the function f of x. And in this particular case, it's the function f of x equals 1 over x squared. And we're going to measure the area underneath that function, starting at 1 up until some other number that we later pick. And so I could see that the way to measure that would be the definite integral from 1 to the arbitrary number t of 1 over x squared dx. And so then t becomes the independent variable in this area calculation. So this is the area as a function of t. What we're going to examine here today is what exactly do we notice about the value of this area function as t increases further and further away from 1. It would make sense that the area would continue to get bigger, but we're going to look at that a little more carefully now. So let's actually write out an expression for the area function that doesn't involve writing a definite integral symbol. What we're going to do is just use the fundamental theorem of calculus. In other words, write the antiderivative of this function. And I encourage you to work that out yourself. But I see this as x to the minus 2, whose antiderivative is negative x to the minus 1. And so we're going to be evaluating this from 1 to t. So inserting t, I get negative 1 over t. Inserting the 1, I'm going to get negative 1. So essentially, if I rewrote this a little more, negative of negative 1 is 1. I could really write this area calculation as 1 minus 1 over t. So in other words, I've now defined the area as an explicit function of t. A of t equals 1 minus 1 over t. Well, let's look and see what happens here as I evaluate that area for different values of t. Well, obviously, if t is 1, the area should be 0, because remember in the original definition of this function, it was the integral from 1 to t. So if t is 1, it would be the integral from 1 to 1, and that would be definitely 0. As we move across, though, if we were to define the area from 1 to 5, the integral from 1 to 5 would be found using this explicit rule now. So this would be 1 minus 1/5. In other words, 4/5. And moving right along, if I were to integrate straight from 1 to 10, I now could just use my explicit rule, and the area I know will be 1 minus 1/10. And then 1 minus 1/20, and so on. Well, one observation here is that the further I go out to the right and I go and define this area as an integral from 1 to t, my final answers here would be 0, 4/5, 9/10, 19/20, 49/50, 99/100, and finally 999/1000. I hope you're seeing a limit occurring here, that the values of this area are approaching 1. And I'm going to keep being able to get them closer to 1 because the amount that I'm subtracting here is a fraction that's approaching 0. So interesting development here. Turns out I can shade in underneath this graph as far as I want to, and the area that I shade will never be above 1 unit, and it's going to approach the value of 1 unit squared. So interesting that this seems like an infinitely long distance that I'm going here, but I'm not going to be shading in an infinite amount of area. It turns out I'm proving here that the area that I shade in will never exceed 1 square unit. And this leads to the notion of what we call an improper integral. In this first sense, we're defining a definite integral starting from a specific spot and just going indefinitely in one direction. In this case, I've demonstrated that going indefinitely to the right here will not lead to an infinite area. In fact, it's going to have a finite area approaching the value 1. So let's look at 3 situations that are like that. We just saw situation number 1. I have a positive function, and I'm starting my area measurement at a positive value a, or really at any number a, but I'm going to continue to shade under it, moving to the right. And so I could define this area accumulation this way, as an integral from a to infinity f of x dx. I'm going to keep shading and shading and shading indefinitely underneath this forever and see what happens. I could define that as a limit because I'm just letting the upper limit of this integral grow larger and larger and larger. So I'm going to actually define this to be the integral from a to b, where b approaches infinity, and we'll be seeing if that limit exists. Now I could go the other direction. If the function remains positive going the other direction, I could start here at b and go toward a. And this time I would let a approach negative infinity, and then my integral would be from a to b. And so I'm going to be shading all this to the left, and I'm going to observe and see if this limit actually exists or not. Now, if my function stays positive the entire domain, I could actually set up what we call a double improper integral, an integral from negative infinity to infinity. Now, essentially what we'll do this time is we'll split this into 2 integrals, one of each of the above kind, by just picking an arbitrary number on the number line. We'll call it c, and we'll set up an integral of type 2 first to go from negative infinity to c, and then we'll make an integral of the first kind from c to infinity. And then we'll just, if those 2 limits exist, we'll add them together, and that will be the value of the double improper integral. If either of those integrals doesn't exist or is infinite, then this whole original integral is infinite. So we have a couple of vocabulary words to describe this situation. If these limits exist, we will say that this improper integral converges, and it converges to its limit. If the limit doesn't exist, most likely the limit is infinite, and we will say the integral diverges. Well, let's take a look at a couple examples here. So here I've got an improper integral of 1 over x from 1 to infinity. I'm first going to just confirm that this satisfies the situation, and that is we need to have an all positive function on the interval we're studying. So this is from 1 to infinity, so x equals 1. And we know the function 1 over x kind of does this. Starts at 1 over 1, and then will gradually decrease to 0 here. Okay, so what we're going to attempt to be doing here is shading under here, but going indefinitely forever this way, and seeing if we get an infinite area or a finite area. Well, I'm going to rewrite the problem now as a limit. It's going to be the limit of the integral from 1 to b, and then we're going to let b approach infinity of 1 over x dx. So let's now write this using the fundamental theorem of calculus. The antiderivative of 1 over x is the natural log of x. And we're going to go from 1 to b, but we're going to take the limit as b approaches infinity. And so we'll now express this limit in terms of b. It's going to be the natural log of b. And I'm not going to use absolute values now because it's understood that b is a positive number now, minus the natural log of 1. And we're going to take the limit as b approaches infinity. Well, now the natural log of 1 we know is 0. And so what this is going to come down to is the natural log of b, where b approaches infinity. Well, we should understand that the natural log of 1 is not as big as the natural log of 10, and the natural log of 100 is bigger than that, and the natural log of 1,000 is bigger than that. So this logarithm function will continue to get bigger, and so therefore this limit is infinite. And so my conclusion is the integral diverges. Interesting that the shape of this graph is very similar to the one we just looked at a minute ago, which was the function 1 over x squared. But in that integral, the area converged to exactly 1, where in this very similar graph, we're going to get infinite area as I shade further and further to the right. Let's take a look at one more, and then we're going to try and make some conclusions about what we've seen here. Let's try 1 over square root x this time. And so I'm going to first rewrite it as a limit, the limit where the limit as b approaches infinity of the integral from 1 to b. And I'm going to go ahead and write this integrand as x to the negative a half to get ready to use the power rule. And the antiderivative of x to the negative a half is x to the positive a half times 2. And we're going to go from 1 to b and let b approach infinity. Okay, so essentially this is going to, it's 2 square root b minus 2 square root 1. And we're going to take the limit as b approaches infinity. Now, once again, the square root of 1 is smaller than the square root of 10, which is smaller than the square root of 1,000,000 and the square root of 10,000,000. The square root function will continue to get bigger, and then subtracting 2 here is not going to make a bit of difference. The limit is infinity minus 2, which is infinite. So once again, integral is going to diverge here. Okay, so now we've seen 3 examples so far. One was used to introduce the topic, but then the other 2 we worked out thoroughly like this. And let's take a look now at what we might see as some important observations. All 3 of those integrals we saw today were of the form 1 over x to the p from 1 to infinity. The first one we saw today was the function 1 over x squared. And it was the integral from 1 to infinity. And by making the table, we actually were able to observe that limit, that integral actually converged to 1, but more importantly, just that it converged at all. So notice in this one, the p-value, according to if I'm running it like this model here, the p-value was 2. Then we saw one where p was 1. It was the integral from 1 to infinity, 1 over x dx. This is the only time when p is 1, this is the only time where this integral does not use the power rule. This is the specific one that follows the logarithm rule, but we saw that this one diverged. And then we tried one when p was 1/2, and we had the integral from 1 to infinity, 1 over, it was the square root of x, but I'm going to call it x to the 1/2. And that one diverged too. So now, breaking down the examples here, when we worked them out in detail, the top one and the bottom one, we used the power rule, worked out the antiderivative, and we found that when the p was 2, it converged. and when p was 1/2, it didn't, it diverged. And now kind of the one in the middle is this one. This one is the only one where we didn't use the power rule, we used the logarithm rule, and it diverged also. What I'm thinking here is that if I'm asked for what values of p will this type of integral converge, I'm thinking that anything where the p is bigger than 1, if I were to use the power rule, I would end up with an expression that I could find the limit of, and therefore the limit would converge, or the integral would converge. But anytime p was 1 or smaller, we ended up with an integral that diverged. And so I believe that is true all the time. We're going to make a conclusion on the next page and write this as a theorem. This integral from 1 to infinity of x to the p, 1 over x to the p, will converge if p is greater than 1, but it will diverge if p is less than or equal to 1. Now notice we're not saying what it, if we're saying it converges, we're not saying what it converges to, but we're just saying it's going to converge at all. We could conclude right away that it's going to diverge if the p is less than 1. A couple important notes, this is only for the integral from 1 to positive infinity and nothing else. However, changing this 1 to a different number like 2 shouldn't change the conclusion. If it's converging, it would change what it converges to, but it wouldn't change that it converges at all. Okay, so really, to make a note of that here, this 1 could be any other positive number. It wouldn't affect anything as far as the converging or diverging goes. Well, let's look at one more for today. This is and now we're going to integrate from negative infinity to 0. I've even drawn the graph this time and showing you that, okay, the function is not always positive, but it is always negative. It's not changing signs at all. So this still applies. It's the integral of x e to the x. Now, the problem here is finding the antiderivative. So let me remind you, this is a product of two functions. And the strategy you just learned is going to help you get this one. The antiderivative is going to require that we know integration by parts. And so we're going to work out the integral by parts first to find the antiderivative before I write this as a limit here, or before I solve the limit. I'm going to write it, though, the limit as the lower limit a approaches negative infinity of the integral from a to 0 x e to the x dx. So I'm going to remind you of a method we just saw the other day, and that is to make a table and set up the u and du and the dv and the v as we go here. And I'm actually going to do that right here, because this integral by parts, our guidelines would suggest that we should let the u be the x and differentiate down here until we get 0, and dv should be e to the x, and then its antiderivatives will continue to be e to the x. We multiply u times v every time. Don't forget to change the signs. So my antiderivative is actually going to be positive x times e to the x, and then minus 1 times e to the x. So that is my antiderivative. I'm going to integrate from a to 0, and then we're going to take the limit as a approaches negative infinity. Okay, so now we're going to write this expression in terms of a. So we're going to first insert the 0. And then we're going to insert the a. And then we're going to be taking a limit as a approaches negative infinity. Well, let's clean this up a little bit, especially on this side. 0 times e to the 0 would be 0. And then e to the 0 is 1. So this whole expression is minus 1. And then I've got minus a, e to the a, plus e to the a. All right. Let's look at the limit a little further now, the parts that involve a. If a approaches negative infinity, e to the negative infinity actually is 0. Remember that. E to the negative infinity should be approaching 0. So that means I can eliminate this guy too. That's going to be 0. So it's really going to come down to now is 0 minus 1 minus, and now I'm just going to put my limit right here and examine this piece. Okay, so the whole convergence of this integral is going to come down to this limit right there. If that limit exists, I'll just subtract the answer from -1, and that'll be my total. If that limit is infinite, then I'm going to get a diverging integral. So let's look carefully here. A is approaching negative infinity, and e to the a is approaching 0 because it's e to the negative infinity. So this is in the form negative infinity times 0. And look out, that's a form that is indeterminate. We learned how to handle that when we were studying L'Hopital's rule. So we have another little lesson here to talk about. And so we're just going to look at that limit on its own. Now on the side to finish this off. So I refer you back to the lesson on L'Hopital's rule. How we handled the form infinity times 0 was we wrote it as a quotient of one of these functions over the reciprocal of the other one. I strongly encourage you to choose this way. Let's write it as a over e to the minus a. Now, and that way I get the form negative infinity over infinity, because now this would be on the bottom, e to the positive infinity. But assuming that I get infinity over infinity or something with negative infinity over infinity, I can now use L'Hopital's rule. So we'll take the derivative of the numerator, which is going to be just 1. The derivative of the bottom is negative e to the negative a. And that now is approaching the value 1 over negative infinity. In other words, 0. Okay, so we're finally ready to figure out the conclusion to our improper integral. It was going to be -1 minus the value of this limit, and using L'Hopital's rule, that limit was equal to 0, and so now the entire integral is equal to -1. Let's see, that makes sense because the area under this curve should be a negative number if I'm integrating from left to right as I was doing. So the negative number doesn't concern me, and it turns out that is the value of that integral, -1. We're going to pause the video here today. Sorry, it was a little bit on the long side, but hopefully this will help you get started on improper integrals. There'll be one more video later on that will talk about a double improper integral.